All right, we're in 8.2 today. This section is not too bad. Okay, we're mainly, so the title is displaying data. The main idea here is we're reading some different types of graphs, so it's not too calculation heavy again. So not a real bad section. Okay. I mean, if you're really good at reading graphs already, it might be a little boring, okay, but it's not too bad, not too difficult anyway. Okay. So let's look at a few here. So the idea when we make a graph is that we want to communicate something, okay, some piece of information. We want to communicate that really as quickly and as clearly as possible. Okay. So there is this idea where you can have a good graph or a bad graph. Okay. We get into that in 204. We don't quite get into it in here, but not all graphs are created equal. Okay. And we're going to just look at a few of the most popular types of graphs that you'll see. Okay. So we just want to be able to read these things, interpret what they're telling us. So it's kind of the next step in our process. So last time we talked about collecting sample data. Then whatever we find in our sample data, we want to be able to communicate that. Okay, so that's where our graphs come in. So you might not think about this first thing we're going to look at as a graph, because it's not necessarily a picture, but it is a visual display of data. So first one we're going to look at is called a frequency distribution, and we will see a more typical graph version of this in a little while. So the idea of a frequency distribution is that we list out the possible values that we get out of our data, and then we just have a count beside each one of those about how often that data value occurs. So that count is what we call the frequency. How frequently does that data value occur in our data set? Okay. So let's take a look at one. Okay. So this one gives us frequency distribution that shows the number of crashes with roadside objects along State Route 3 in the state of Washington. And then we have a few questions. The whole thing wouldn't fit on here, so there's the first 3 rows. So we've got the whatever type of object was involved in the crash, and then I got the number of crashes, the frequency for that category here. I've got some more on the next slide. Okay. And if we had any weird ones on there. Luminaire, that's just some type of light. Street light, maybe. And then I think we may have a few more rows. Let's see. Yep. Kind of surprised mailbox is not higher on the list. I don't know the area in Washington where this road is, so maybe there's not a lot of residential area there. Okay, so there's our frequency distribution. We've got a few questions to answer. Let's see what we want to know. The first one says, what do the numbers in the parentheses tell us? Okay, so talking about these numbers, it's on there. They've got it listed. So just the numbers outside of the parentheses are the counts, just how many of these objects were in our data. And then the numbers in the parentheses tell us as a percentage of our data set, what percentage of people had collisions with those types of objects. So 11.32% of people in our data crashed with a tree, okay, crashed into a tree. So what kind of stuff that tells us? Okay, so let's look at the next one. Part B says, which roadside object was involved in the most crashes? So they're in order here, so we'll have to go back to the beginning. Okay. So biggest number of crashes, that was with a guardrail. Okay. 15.36%. Nothing too amazing there, but we're just answering the question. And then C, ask us how many total crashes the survey covered. So we want to know how many total crashes we had in our data. How could we figure that out? It doesn't give it to us straight away, but we could figure it out. Yeah, so we would just have to add all of our numbers out, right? These are the counts for each category. So we would just have to add all those up. It's really inconvenient on this one because they're not all together, so I won't make us go through it. And we're just adding up the number of crashes in each row. Okay. And let's see how many we get there. 371 if you add them all up. Okay. Just to add up all the frequency. 371. Okay. Let's look at another one. So on this one, we're going to start with the data, and then we'll see how that gets turned into a frequency distribution. So this one says a number of household pets for 52 families is recorded. We want to make a frequency distribution of the data collected. So we won't go through every little detail of making the frequency distribution. We just kind of want to get the big picture here. So what we would have to do is we would have to make a row for each possible data value, for each possible number of pets. And then we just count how many belong to each row. So like our first row, we could start with the most or the least, would be the typical way to do it. Here it looks like 0 would be a good place to start. So if we count how many households had 0 pets, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So our frequency for 0 pets would be 16. And that's all we're doing. We're just counting how many data values we have in each one. So if we did that for all the different possible number of pets in our data, we would end up with a frequency distribution like this. So 15 households had 1 pet, 13 had 2, 3 had 5. 5 had 3, sorry. Okay. 2 more questions here, let's see. Or just one more, sorry. Someone said, what's the most popular number of household pets in our data? So what was the most common number of pets? 0. Yeah, 0. Okay. And then a lot of people with 1 or 2, and then it starts trailing off. Get up there. Huh? Anybody in here have more than 6? No? Okay. Sometimes you do, yeah. Some people have a little mini zoo at their house. Okay. So that's frequency distribution. Most of the time, we don't see just a regular frequency distribution like this. More commonly, we'll see what's called a grouped frequency distribution. Okay, so a grouped frequency distribution, instead of having a different row for every possible data value you can get, it will put them into groups. Okay, so with our pet example, maybe we would have a row that said people that have 0 or 1 pets, and then we would have 2 or 3 pets, or 4 or 5 pets, right? We would group them together. So if we have more than one data value that can go in a particular row, we get a grouped frequency distribution. And each one of those categories we make when we're grouping our data values, we call those classes. One thing that's important when we're grouping our data is we want each class, each category, to have the same width. So we want them to cover the same number of values for each row. That width we call a class width. And we don't let them overlap. And then the smallest value that can go in each category we call the lower class limit. And the biggest value that can go in each category we call the upper class limit. So let's look at a group frequency distribution. And I've got these slides on Canvas too, if you need them. Let's look at this one. We're going to look at the number of text messages used per month for 52 individuals. Tells us to construct a grouped frequency distribution. And so, idea is we would split our data up into categories, right? Each category is going to be the same width of each class. And then we'll count how many data values fall into each class. Again, we're not getting into all the little details about how you decide how many classes and all that. It's typically nowadays you would let software do it. Okay, Excel will do this, and all kinds of other software will do this. So we won't get too deep into all the little details. But if we split it up into categories, counted how many we have in each category, look something like this. Okay. So that we had one person that sent between 130 and 179 text messages. We had 3 people that fell in the range between 180 and 229. That's all that's going on there. We're just counting how many are in each one of these data ranges. Okay. Talking about our vocabulary, the numbers over on the right, these are our upper class boundaries. Or limits, sorry. Class boundary, something else. Okay. So you'll have questions like, what's the upper class limit of the third class? And it starts here, so 1, 2, 3. So the upper class limit of the third class would be 279. Or it could ask you, what's the lower class limit? Those are these values. It's the smallest number that can go in each category. And then one little easy calculation we want to be able to do. We could have a question that says, what's the class width of these classes? So we said the class width was how wide each category is, each class. You do have to be just a little bit careful. You may be tempted to look here and say it's 49. If you do that, you're missing one thing, because the way we need to subtract is we need to take like 2 upper limits or 2 lower limits that are next to each other and subtract those. So if we do, we'll do the easy one. If we do 330 minus 280, then our class width is 50. Because you have to include the 130 if you're subtracting. So instead of 49, it's really 50 is our class width. Okay. You can do the subtraction with any 2 consecutive upper class limits or lower class limits, and you'll get 50, because they all have to be the same width. So you'll get the same thing no matter which 2 you choose, as long as you choose 2 on the same side, right? Either 2 lowers or 2 uppers, and then they have to be consecutive classes. Get that one. Okay. Questions on that one? Nothing too bad. Okay. Another really popular type of graph, I don't even have an example in here because I'm sure you've seen one, is pie chart. So just really quickly, the idea, okay, is that a larger slice of the pie means that whatever category of data you're looking at that has that slice takes up a larger portion of the data. So we're thinking percentages when we're dealing with a pie chart. So a larger slice means that's a larger percentage of the data. So I don't know that I've ever met anybody that hasn't seen a pie chart, so we won't spend a whole lot of time there. Okay, another one you've almost certainly seen is a bar graph. Okay. So with a bar graph, the longer or the taller the bar is, the more frequently that data category occurs in our data. So not a whole lot to talk about there. Let's look at one. Okay, so one gives us 4 categories for 4 different generations of people, and then they've asked these people the question, do you consider the United States to be the greatest country in the world? And then we've got the percentage of people from each generation that said yes. Okay. So which generation was the most likely to think the United States was the greatest country in the world? Silent generation, yeah, silent generation. Okay. A lot of you are not even on there. Yeah. Textbook's getting a little old. Okay. We got Gen Z on there. Some people are starting to call Gen Z Zoomers. Okay, so kind of taking off. I'm like kind of in between these two. There's a little, the one I identify with the most, I call it Xennials. Well, if I can write. A little micro generation there. That's the one I feel like I'm more part of. So kind of in between here. Any questions on reading the bar graph? The Xennials had video games, but we still played outside. That was the main thing. Okay. Okay, let's see. We got those. All right, with bar graphs, you can also, if you want to compare different groups, you can also make what's called a side-by-side bar graph. So the idea there is that we have 2 or more different groups that we want to compare, and we can make a bar graph for each group, and we put the bars for each category right beside each other so we can kind of compare and contrast. So this one's a little technical. So here's the main idea. Okay, we don't have to get into all the details here. They've got this group where they're researching cancer rates, called SEER groups, SEER areas, and we're comparing some demographics of these SEER areas, okay, compared to just the United States as a whole. Okay. So remember, when we're trying to answer a question, like we're trying to do some research, we want our sample data, right, to look like our whole population. And so ideally, these bars would match. If we look at the people in the study, the SEER areas, what can we see? We've got more people born in other countries in our research group than in the United States. We've got more people that have less than a high school diploma than in the United States. Below the poverty level, they're about right. SEER group's just a little bit lower than the country as a whole, so we can compare, right, what's going on in the two different groups with that side-by-side bar graph. Let's see what's next. Another way we can do a similar type of comparison, instead of having a side-by-side bar graph, you may not have seen one of these, is we can make a stacked bar graph. And they don't come up quite as often, okay, but they can be really useful. The idea is the same as a side-by-side, but with the stacked bar graph, we'll put the bars on top of each other and use maybe like two different colors to show which part of the bar is from which group. Okay. So just, you'll know what to call it if you see one of those next time. Okay. And then last one here, I think, let's see, is this the last one? Yeah, last type of graph we're going to talk about, okay, called a histogram. Okay. And a histogram is what we get when we take a frequency distribution and turn it into more of a traditional graph. And then we get a histogram. And so we're kind of thinking back to those frequency distributions we talked about at the beginning. We just take the frequency at the count of how many data values we have in each category. That tells us how tall to make the bar on the histogram. And one thing that's unique to a histogram over the bar graphs we've seen is the bars touch. Okay, we don't have any gap in between them. So let's look at this histogram and answer some questions about it. All right, we've got a histogram. We have some data from delivery truck drivers. They're recording their wait times at delivery places that have closed entrance gates. And so we want to know how long they have to wait at the gate before they let them in. And here's our histogram. It's a little small there, so I've made another slide with it a little bigger here. So let's think about some questions off of this graph. Again, they're not too tough. Let's see. So A says determine approximately how many truck drivers were in the survey. And we're just estimating, right, based on the height of the bars. We do have a lot of bars we have to estimate here. Let's see. This first one I would say is about 15. What do you think on the next one? Yeah, 48 sounds maybe like 28 on this one. Next one's really close to 20, so probably 19. What do you think on the next one? Yeah, probably about 17. This one's right on 10, it looks like. So the next one, yeah, it's probably got to be 9. Yeah, probably 15 again on that one. Another 9 and 8 maybe, yeah. Yeah, that one's either 12 or 13. I'm leaning a little more toward 12. Yeah, maybe 19 again. Yeah, if we call the other one 12, we would call that one 13, I think. And then, what was that? Yeah, either 12 or 11. We'll call it 11. We said estimate, so it's okay. And then last one, I think, is about 5. Right? So we would just add all those up. So let's see about what we get here. Kind of an annoying question because we have so many bars, but it's not hard, just a little aggravating. Did I skip any? Let's see. Ten, 9, 15, 9, 8, 12, 19. Okay, so I got about 238. So something like that. Okay. histogram's not the best way to get that information. If you were trying to communicate that to people, that would be something you would want to put on there. You'd want to have a total size if that was important for them to know that, because it does take a little time to go through and figure all that out. So sometimes you'll see a bar graph and it'll say something like N is 238. It gives you the total number. Okay. So somewhere in that range, we may be off 1 or 2, that's okay. Let's see, B says approximately how many drivers waited between 60 seconds and 180 seconds. So 60 starts at the second bar, and then 180 goes up to the fourth bar. So we really want the second and the third bar. So we would add those two together. So what is it, 76? Okay. So we got 48 and 28, so that's everything is about 76. Okay, we said 238 on this one. Okay. C throws us a little bit of a curve, and you've got these in the assignment. Okay. C says approximately what percentage of drivers waited more than 7 minutes. Okay, so got two things going on. We need to figure out more than 7 minutes, and then we need to answer in percentage. So, oh, wrong way. So 7 minutes, since we're in seconds here, 7 minutes would be 420, yeah. So more than 7 minutes would be this bar up. All right, so let's see, let's add those up. So we're adding from here up, so 15 plus 9 plus 8 plus 12 plus 19 plus 13 plus 11 plus 5. Whoa, I didn't clear my calculator before I started, so that was way off. I got 92. So I got about 92 truck drivers that waited more than 7 minutes, but we want it as a percentage. So how can we get that? We need to divide by the total. We said that was about 238. And then now we're kind of back to the last test, right? 92 divided by 238. That's 0.386. And it goes on and on. So we would say, it doesn't tell us how to round, so we'll just round to the nearest percent. So about 39%. Something like that. So we just take the number we get divided by the total and change that to a percentage. Okay. Questions on that one? Can't think of anything? All right. That's it on 8.2. Okay. Short section. Okay. Short section. All right. If you didn't get on the sign-in sheet, make sure you get on there before you leave. Somewhere floating around. If you want another piece of candy on the way out, grab another piece or two.
Hard decisions, man.
Yeah, I try to get a good mix. So. You're welcome.